Okay, hi everyone. First of all, thanks Martin and thanks the organizers who invited us to present work, what we have done in the last several years. So today we are going to talk about food information extraction and normalization, the past, the present, and what we are thinking that will be the future. So when we got the invitation and we think about, okay, what we need to present there, what kind of, which actually publication to select, how to present the work we have done, actually, I realized that I need a help and I cannot provide the presentation alone. So I invited one of my friends to make a joint presentation. So Gjorgjina Cenikj is today here with us. So she will help me to provide this presentation even better, what I can do alone. So first of all, again, thank you for the invitation. What we are going to cover today. First, you already all know here at the workshop, we talk about data, we talk about information, and we talk about knowledge. Then we are going to provide an overview of the BioNLP workshops which are going during the years. I think Martin has already done in the introduction talk a really nice overview of what is actually existing, different shared tasks, different initiatives that are going around, the NLP, which is applied biomedical domain. And then our focus today actually is going to present the food information extraction, focusing on 3 different periods, what we call the past. And then we are going to talk about 2 methods like Dr. Nair and Stand Food. Then the present, which is Foodie, FoodBase, Food on Tome Eftimov, and DietCup. And at the end, Gjorgjina is going to provide information about the future, which are actually some methods, which are butter, Food Nair, Saffron, FoodBase, FoodHam, and so on. You will see from the presentation. At the end, we are going to end up with some discussion. So if you have questions, please feel free to ask us here or just ping us in email. We are happy to answer and help with the work. So you already know we are talking about data, information, knowledge, and wisdom. So especially when we are doing textual analysis, we have the data. Once we have the data, we need to extract some information. For example, imagine we are doing the electronic health records. We are talking about to find what are the disease, drugs, what are the symptoms. So we need to extract this information from the data. And once we have this information, actually what we are doing, we are extracting the entities, we are linking the entities to some semantic resources. So we got some information, we have some normalized data. Once we have this, we can think about doing predictive healthcare modeling or doing some deep neural network LSTM models from longitudinal data for predicting some diagnosis at the end. So what is the idea? Our talk today actually is focused only on the first 2 levels. So we want to, we are going to provide different methods that can be used, how from data actually we can get this food and nutrition information. And our use case is especially in food entities which are there, but you will see how they can be also linked to some chemical entities, to some disease entities that appear in scientific abstracts and so on. So, why we started working focusing on the food entities, exploring nutrient content is crucial for several aspects. We already saw today at this workshop. So we have patients which are suffering from different diseases. From other side, we have the professional athletes and also everyday life for many health or fitness goals. So today we have a lot of data which is coming. For example, imagine when we are talking about food consumption. When we have the food consumption, it's not like the past. We are not feeling this food frequency questionnaires 24 recalls. We are still doing this in some studies, but actually everything is going to some digital dietary assessment. So it's much better, or even in social media, what we are doing, for example, we are going to some lunch, we are going to some breakfast, we are taking picture of our food, we are posting this on Instagram. So we have a lot of data which is coming about our food consumption. From other side, we have the food composition databases. So the food consumption should be linked to the food composition database to calculate some nutrient values. We all have all these smartwatches, which we have some different signals which are coming. So all these data can be linked together. And then we can talk about some exploring relations between some health concepts, between some food and nutrition concepts. And also we can explore relations that exist between food concepts and some environmental concepts. So as I already said, we have different type of data which is here. We have some signals data. We also have some textual data. We can have, for example, the food composition data are structured databases. And also from other side, if we want to make some normalization, we have the semantic models, which are the ontologies, and we can treat them as some graphs or to be like to following the new terms, we can talk about some knowledge graphs. So today for this workshop, even we have studied some predictive nutrition and food studies which are already developed here, but today we focus only to talk about like text data, and also talk about only name entity recognition and name entity linking stuff. So the idea is to focus only on the language technologies. So as I said before, like we have the information extraction task. I think that there is no reason why to to introduce the task again. So we distinguish two different tasks. We have the name entity recognition. For example, if we have excessive salt intake have been associated with a higher incidence of heart disease. So the idea is to extract like what is the food entity here, and then, for example, in our case, what is like the disease here. When we have the name entity linking, we have one level up from the name entity extraction. So we are extracting the entity, but instead to be standardized or normalized like this it is, we need to link them to some semantic models that already exist. So for example, in our case, the salt will be linked to the, in our case, we provided the link with the Foodie database. And also if you want to have the heart disease, we talk about like, we provide the QE, which is coming from the UMLS. So we have like two tasks. First, extract the entities and then link the entities to some semantic model, because further this information should be used in some like predictive studies. So we have the information that should be used for predictive healthcare. Let's see what happens with the BioNLP shared workshops during the year. So there are several BioNLP workshops which are going, for example, BioCreative, BioNLP. And on this slide, actually, we have a really nice timeline where you can see like the progress, what were the entities of interest starting from 2004 till 2021. And if we make a summary, actually, we can see that there are like several entities which are interested, because this is from the biomedical perspective, from the bio perspective, sorry. We have gen mentions, like protein mentions, protein-protein interactions, chemical name entity recognition, then chemical drug relation extraction. And in 2021, there was at BioCreative, if I'm not correct, Martin, please correct me, but it was some task which was related also to COVID-19 literature mining. So this is what happened on the bio side. And then we have also some clinical information extraction during the years. Martin has already presented in his introduction talk a lot of these shared workshops. We just put like two of them, like I2B2. There is also at ACL clinical name entity recognition workshop. I think the third edition was this year. And the people are interested in some symptoms, disease, drug, treatments. And now what is the idea? We are talking about a lot about these annotated corpuses and everything. So during my postdoc, I have experience actually to work on a lot of medical data, like electronic health records, patient-reported outcomes, scientific articles, where the idea was how to extract actually all these different clinical entities. And what is the main problem? The main problem was that you all know here, like the writing style. So it's completely different if you have model like name entity recognition model, which is trained on an annotated corpus, which work on the electronic health records, which are written by medical persons. And if you have patient-reported outcomes like diagnosis as something which were reported by the patients, the model will not have a good transfer learning results. So this is one aspect we should think about as a community, how to care about, like how to have a representative landscape of our data sets. Because at the end, the model should be transferable. We are doing this in order to track this for some future application scenario. So in the clinical domain, this is possible actually to be done, all these disease, treatments, symptoms, like what we can extract it. You all know about the Unified Medical Language System, which is a set of files and software that brings together many health and biomedical vocabularies and standards to enable interoperability. And actually, there are a lot of resources. First, for example, this allows first to develop some dictionary-based, rule-based approaches, to have some silver standards, then to go like creating golden standards with the help of the subject matter experts. And at the end, when we have the golden standard, then we can train some corpus-based natural language processing. Or, for example, at the recent years, we can reuse some of the recent advances when it comes to the transformers. So let's talk about first in a general way what we have from language technologies to decision support. So what we need to do, if we have some textual data, which is a raw data, first we need to perform name entity recognition, like extracting our entities. then the next step, because our data is not normalized, standardized, we are performing name entity linking method. The next step, if we want to explore the relation, we have, okay, now we are able to do the name entity recognition, name entity linking, but it comes to the relation extraction. Define the pairs of entities, like, and train a supervised machine learning model in order to extract relations between the entities. After having this, we are able to provide some having this kind of methods actually allow us to do some semi-automatic knowledge-based construction, or with the help of the subject matter expert, we can provide some golden standards, and we have some structured knowledge. So we have from textual data, we went to some structured knowledge. Having this information, as I talked before, as I talked on the first slide, like when we have data, information, knowledge, now having this information, actually we can train some question answering system, we can develop some decision support, which is actually the main of the studies, which is the motivation of the studies actually we are doing. We are developing these methods in future to make impact to the society. Okay, so where are we now when we think about the biomedical domain? So the biomedical domain is so well explored, a lot of vocabularies, a lot of annotated corpus are there. Each year we have like a new annotated corpus which is coming, which is filling some small gaps, like when we are developing such kind of methods. And we are possible to do like the automatic knowledge-based construction. We have some structured knowledge, and now even more like more interesting information are coming. Applications, sorry, are coming in the question answering, or are coming in the decision support. So people are reusing this information we are actually obtaining with the natural language processing methods like name entity recognition and name entity linking, and are able to provide some decision support tools which are used in some clinics, which are used like by the biomedical scientists, or even more in some industries. So we are able to do this today. Even there are a lot of gaps, and each year we are trying with new corpus to solve some specific gaps which are covered in the landscape of the annotated corpus we have. Actually, we are able to do this. But let's go now to the food domain and think about only food entities like food products. What we need to do is actually, we are still struggling here, name entity recognition methods and name entity linking methods. So today we are talking about only the first two steps. And also Gjorgjina will provide some information about the relation extraction methods, but now we are developing methods in order to have some semi-automatic knowledge-based construction. We are still not in the way to provide some question answering, decision support. We can do this, but actually in order to make them better, this kind of application, we should first think about to have a really nice annotated corpus and methods that work like to extract the information and further to link this information to the semantic models to create this knowledge base, and then the knowledge base to be reused for future. Okay, so today we split the presentation on these three parts. So I'm going to present the past and the present, and this work actually starts from 2017, which 2017. And first, the past are two methods, like Dr. Nair, which is a name entity recognition method, and StandFood, we can assume that StandFood is a text normalization method and actually link the food entities to the FoodX2 system, which is actually developed by European Food Safety Authority. When we come to the present, we are going to talk about Foodie, Food on Tome, FoodBase, Food and DietCup. Foodie is a name entity recognition method, and we have several resources semantic which are developed to allow like the interoperability. And at the end, we have DietCup, which is again some text normalization method. And after me, Gjorgjina will provide like information about the future, and she is going to explain the butter, the saffron, the FoodNair, the Foodies, FoodChem, and everything we are planning to do like the next year and in future. So this is the pipeline we are going to talk about today. And before we start, actually, I would like to give an overview of the food semantic resources, which are most highly explored like in the food domain. So first of all, we have the food ontology, which in my opinion, like it's the most commonly used, and it's well known at least by the food scientists. Then we have some Hanser taxonomy, which is developed by the one project, USIS Semantic Tagger. Then we can have the SNOMED City. And why SNOMED City is really important? Because people who are doing the biomedical domain, you already know that when we have SNOMED City, for example, we can extract also the QE from the UMLS, and actually we can easily link the food which exists in the QE to some SNOMED City, and we can explore if we standardize data with regard to the SNOMED City, or to UMLS, then we can easily explore relations that exist between food diseases, food drugs, food treatment, food symptoms, or we can talk about all of them together, like having a heterogeneous network. And also we have the FoodX system, which is a taxonomy. It's a not semantic model, which is developed by the European Food Safety Authority. And it's a standardizing and classifying system to make each of the food products unique. So what is the past? And it's work which is done in 2017 and 2018. Dr. Nair is a rule-based name entity recognition method for information extraction from evidence-based dietary recommendation. As I said before, we have the Stanford, which is classifying and normalizing food mentions according to the FoodX system, which is developed by EFSA. So what is the idea by Dr. Nair? When we started working on Dr. Nair, the idea was, okay, what we can do, and actually as other groups, we want to have an annotated corpus, which is already in 2000, this work started in 2014, actually. We want to have an annotated corpus with all these food entities, like what is a banana or some, I don't know, an apple, food consumption data, recipe data, scientific abstracts with some food entities, but we are not able, it was, to the best of our knowledge, was not actually presented. And the idea was, okay, when we cannot do a corpus-based name entity recognition methods at that time, and we decided to do with some rule-based approaches. So what was like the key difference of the Dr. Nair as a rule-based approach with all other rule-based approaches, which were developed, for example, at BioCreative in 2014 for the chemical name entity. So we know that all these rule-based approaches actually are dictionary-based in combination with some rule of the entities. So imagine that we are doing like the chemical name entities. So the rules in most cases are coming with the properties of the entities. We know if this is organic, non-organic, alkali, so we know what are the suffixes and the prefixes of the chemical names which are there. So we can write a lot of rules. But in our case, the rules were not based on the characteristic of entities of interest, but actually we are doing some Boolean algebra, and we are doing some Carnot maps, how some chunkings which are candidate for some food entities actually should be merged together. You have claimed to this paper, but actually it was evaluated only on 100 scientific abstracts, which are coming from different journals in order to have difference in writing styles. And the result was actually evaluated by 2 domain experts. So what we were interested, for example, imagine that we have 1 teaspoon of table salt contains 2,300 milligrams of sodium. We are able to extract like what is the nutrient, what is the quantity unit associated with the nutrient, what is the food here. And to catch like the trace of the relations, we use the subject-object predicate. Like for example, here we know that we have a quantity unit 1 teaspoon, which is a subject. And this is related to the table salt, which is the food entity, and it is in the subject of the sentence. So we were able to provide something like this, or actually, these are some dietary recommendations. If we have, for example, good sources of magnesiums are fruits or vegetables, nuts, peas and beans, soy products, whole grains and milk. Actually, we are able to have this food like fruits or vegetable, nuts, peas and beans, like one food chain, like, and not separate food entities. So we have pretty much good results. This was the first attempt how to extract the entity unit, the nutrient, the food. Like also we were interested in the population group. So it is really important if this is for babies. For example, you have the pregnant woman, you have completely different populations. Even more now thinking about personalized medicine and personalized nutrition, we can also personalize to different like diseases and so on. So this was the first attempt, like when we try to do the name entity recognition, focusing on such kind of entities which are related to the food domain. And further, when we extract the food entities, we were interested only in the food entities and how we can link them to the FoodX2 system. And for this purpose, we proposed the Stanford, which is actually a method. It has 3 parts, but the main part, which is important for us, is the description part. So what we can do here is actually the lexical similarity. And when we have the lexical similarity, we are doing some morphological analysis, like part of speech tagging, finding like what is noun, verbs, and adjectives, and then the information between the description, like we are treating this as a probability event, and it's able to find what is the most closest. So for example, imagine that we extracted some an apple roll, and then we want to match this to the FoodX. What we are doing, we are taking the name, we are actually doing some probability with part of speech tagging, and we are linking this to the database, which is actually published by the EFSA. So these are some results actually, and this was again, we say that this is a semi-automatic approach because for some of the linking we got actually several candidate solution, and then the domain expert should select what is the correct. And what was interesting actually in the description, we got like 79% accuracy. We were testing like the Slovenian food consumption data there, and the percentage which were missed in this linking actually were some traditional foods, and the traditional food do not exist in the EFSA database. So this was one of the weaknesses of this. So it works well, the lexical similarity, but actually we have some still missing information because actually the EFSA database it does not consist like the traditional food for each country. And also we can have, when you think about lexical similarity, you know that the writing style is really important. And now when we come to the present, actually after these two methods, we have like 2019 and 2020, we developed the Foodie, which is again a rule-based approach for name entity recognitions for food information extraction from recipes. And after we have food, we were able to provide the first annotated corpus, recipe corpus with food entities, which is the FoodBase. Then we normalized the FoodBase annotations to the several different semantic models, and we created the food onto map, inspiring by what is done by the UMLS system. And we also provide a human-computer interaction tool for domain expert annotation and correct automatic annotation, which is the FoodBase. And at the end, we develop a DietCup, which is a text normalization method, which uses a multi-label classification method for recipe classification according to ingredient classes. So what was Foodie was extension of Dr. Nel. And the idea was, if you remember when I said, okay, we have, for example, a food chunk, we have several foods which are grouped together. Now with Foodie, we want to have like each food entity to be a separate extraction. Like we don't need to have fruits or vegetables and nuts, like this is a food chunk, but actually we were interested to have each of these food entities which form this food chunk actually together. And then we developed Foodie. Again, it's a rule-based, and actually the rules are again similar to Dr. Nel, but we incorporate like semantic information, which is coming by the USAS semantic tagger, and it provides on a token level information if some token is associated and it's related to some food product or not. So we were able to do this, and we evaluated this on thousands of recipes. Two domain experts checked this information, and these were the results which were actually obtained by Foodie. Like these are the F1 score, the precision, and the sensitivity. So having these 1,000 recipes, because actually we evaluated them, what we have done, we realized what are the false positives and what are the false negatives. And having this information from the evaluation, we actually published the FoodBased Corpus, which is actually a corpus from 1,000 recipes, which are extracted from allrecipes.com. And from different categories, like we have like uniformly distribution across different type of food recipes, like lunch, breakfast, dinner, drinks, and so on. So the idea was like, okay, Foodie extracted all this information. The information was checked. The false positives were removed. The false negatives actually were added to the corpus, and we created the first golden standard. And once we have this was in 2019, and it was published in the database Oxford Journal. Actually, the data set is published in the BioC format. We were able actually to train some of the corpus-based machine learning approaches and recent advances that are doing in NLP. But now the problem was, okay, we have this corpus, and this corpus is actually normalized with Hansard semantic tags. What if I want to do, for example, food information extraction, like food name entity recognition, but I want the semantic tags to come from the SNOMED city, because further my application scenario is to explore some relation with some disease or drugs entities. So what we need to do in this case, we said, okay, let's translate this corpus to some other. How we can do this? Actually, we took all the extraction which are already in the FoodBase, and then we have the Hansard corpus. And from other side, we use the Stanford NCB Annotator, because I was doing my postdoc actually at that group. So we took the NCB Annotator, and we select different ontologies which are already available in the bioportal, and then look at this, how many of these entities which are extracted by Foodie, the gold standard, which is the FoodBase, how many of them also are covered by these ontologies. And actually this kind of experience provide us information how the semantic types, the alignment between the ontologies can be done. For example, imagine that you extracted some information that relate to Snowmed City. We have another group relation which is actually standardized to food on, and now we cannot make data fusion of these two kind of corpuses, right? We need to make them standard. And using this food onto map, which is the idea like what UMLS is using, actually we are able to standardize, to transform the data from Snowmed City to food on, from food on to food X2, something like this. So using this research, it's really easy to go like through your annotation and then to check what is going around and to change like the semantic tags, and to be able actually to have like one data set which is standardized with respect to the semantic model you want to utilize in your application. And because we are doing these interesting NLP stuffs which are behind and everything like this, the idea was, okay, now we have all this, but we need to bring this annotation closer to the domain experts. And what we can do here. For this reason, we developed the FoodBase. It's already published paper in 2019. We have the FoodBased Corpus, which is there. The recipes, all like entities which are extracted, normalized to the Hansard taxonomy, and also to the food on, to the Snowmed City, to the onto-food ontology. And you can go there. Actually, subject matter experts can be involved. They can already change what is there. They can change like, because now we have 1,000 recipes which are golden corpus, but we have 100,000 recipes which are not checked by domain experts. And now actually we have also scientific articles which are we are working at the moment. So this FoodBase is extended with a lot of new features that are published actually in this paper. So this is a nice actually platform where all these methods we are developing previous, like the Foodie, the Doctorner, all these 10-foot normalization methods, which are included as a web services inside, and the knowledge which is providing by this is visible by the domain expert. And further, in 2020, we work on DietCup, which is actually, again, now we have the annotated corpus with food entities. And we want actually to do like, we want to train a model, a corpus-based model. So we use the same recipe. So we use the recipe description, and now we have also, for example, each ingredient which is mentioned there. And we treat the problem as multi-label classification. We want the recipes to normalize to the ingredients which are presented there, or we have a multi-label here like classification task. For the text, we use like the Reson Advantage for representation learning, like BERT, Roberta, XLNet. We also try back of words plus TD-IDF, Doc2Vec, and then we combine all features. And we apply like hierarchical multi-label classification model. And the best results using predictive clustering trees was achieved with the back of words plus TD-IDF. The results are similar for all representation. There is no some statistical difference if you think about this, and some practical difference, but that if you know, when we are doing some machine learning tasks, people are interested for the highest number. So for this reason, we said that these features provide the best results. But what was this study? Actually, this study allowed us to do some COVID-19 impact on food consumption patterns. So if we can actually normalize the recipes to the ingredient level, what we can do? We took recipes that are actually using before the first quarantine of the COVID-19 lockdown, and actually we use the recipes which are used in the first lockdown of COVID-19. And this is a global analysis. The recipes are coming all around the world. So we haven't done even further. We can complicate it. We can make this personalized, focusing on different population and so on. And what we have done, we use this like DietCup approach. We normalize each recipe to the ingredient, and now because we have like normalization to these different Hansard semantic tasks, we are able to do some statistics at the end. And what was the results? Food and Agriculture Organization actually published a lot of like a lot of points what they are thinking that COVID-19 will have impact to the food systems, and all their listed points on the website were actually covered by the analysis. They come from the data-driven approach, and they come from the analysis. And even more, we are always like laughing about this, but actually the most interesting result is that the consumption of the pancakes actually increases for 300%. So 300% is people have done a lot of pancakes when they were in the first lockdown of COVID-19 impact. But what we actually started, we started with some rule-based approaches, and these rule-based approaches provided us like an opportunity to make an annotated corpus, and this annotated corpus further allowed us actually to explore, to create different semantic resources, and also to make some further more analysis. And now I will stop here, and I would like to invite Gjorgjina to continue with the future. So I'm going to stop my sharing, and Gjorgjina take the lead. Thank you.
Okay, so Tome has done a really nice job of presenting the work that has been done by our group in the past few years. And I will now continue with the works that we have done this year. And these have actually been enabled by the resources that we have generated. So FoodBase and Food-on-to-Map have allowed us to now use some deep learning methods and language models, which are actually achieving state-of-the-art results by different users in NLP. So I will present two named entity recognition models, Butter and Plunder, and also Saffron, Foodie, and FoodChem, which are more related to relation extraction. So Butter stands for bidirectional LSTM for food named entity recognition. And it is a corpus-based named entity recognition method trained on the FoodBased Corpus, where the named entity recognition task is treated as a classification task, where the classes are tags from the inside-outside beginning or IOB tagging scheme.
Sorry to interrupt, Gjorgjina. I believe you are not sharing the slides. Okay, great.
Okay, great. Okay, so the Butter model uses the word representation models, GLAB, WordTWig, and PastText, and it is based on an architecture using bidirectional long short-term memory and conditional random fields. And we have explored two model architectures, one of which just uses word embeddings, and the other one uses also character embeddings, which are generated with time-distributed embedding and an LSTM. And both of the models output the probability of a word belonging to each of the tags from the IOB tagging scheme. And all of the models achieve a performance of a macro average F1 score above 0.9. And the best model is actually the lexical lemmatized model, which does not use pre-trained word embeddings, but trains embeddings on the FoodBased corpus. And also we have worked on the Plunder model, which is another corpus-based named entity recognition method, which also can be used to perform named entity linking. It has been trained on the FoodBased corpus, much like the Butter model, but instead of using bidirectional long short-term memory and conditional random fields, it uses BERT and BioBERT models. And this is accomplished by fine-tuning the BERT and BioBERT models on the FoodBased corpus. And actually, we are exploring 5 tasks. The first one being, we call it binary classification, or determining whether a word belongs to a food entity or not. And the second one is a multi-class classification, where the goal is to determine to which parent category of the Hansard corpus a word belongs to. And in this case, we have 48 tags. The third task would be to determine which is the closest tag in the Hansard taxonomy. And in this case, we have 92 tags. And the fourth one is multi-class classification to the food ontology, in which case we have 205 tags. And finally, multi-class classification to the SNOMED city ontology, in which case we have 207 tags. And actually, we can see that the performance on the binary classification task, which is also the task which Butter addresses, Plunder achieves similar performance of around 94%, while on the rest of the tags, the performance varies from 73% to 78%. and this is with respect to the macro-averaged F1 score. So having this type of named entity linking method has enabled us to move to the next step, which is actually relation extraction and automating the process of knowledge-based construction. And this is actually needed in order to structure the information which is present in biomedical scientific literature and to reduce the effort that is required on the expert's part in order to generate these knowledge graphs. So this type of knowledge graphs already exist in the food domain and also in the biomedical domain. However, while in the food domain, we might have knowledge graphs that contain recipes, food and nutrients, and in the biomedical domain, we might have diseases, drugs, treatments, anatomic parts, and such. We are interested in exploring how we can relate these two domains so that we can use both the information about the food entities and their relations to the entities in the biomedical domain so that we can move towards, say, personalized dietary recommendations. So in order to automate this process of knowledge graph construction, we have developed several pipelines that will take care of the knowledge graph construction. And in these pipelines combine three types of method that Tome already mentioned. So we have named entity recognition, named entity linking, and relation extraction. So in this example, we have the sentence excessive salt intake has been associated with a higher incidence of heart disease. And in order to infer from this sentence that the salt entity causes heart disease, we first want to extract salt and heart disease, then link them to some external knowledge base, and then finally apply relation extraction methods to determine the relations that hold between these entities. And going in this direction, we have worked on developing relation extraction models. The first one being Saffron, which stands for transfer learning for food disease relation extraction. And this has been published in ACL this year. And so Saffron is a relation extraction method for detecting cause and effect relations. And here, as in the rest of the models that we have developed for the food domain, the main challenge was the lack of annotated data with respect to relations between food and disease entities. So the idea we explore in Saffron is actually using transfer learning to repurpose the existing resources in the biomedical domain and see if we can use them to extract cause and treat relations between food and disease entities. So we have used two datasets as source datasets in the transfer learning scenario. We have the crowd truth dataset, which contains about 4,000 sentences, which have been annotated for the existence of cause and treat relations between biomedical entities, and also the adverse drug event dataset, which contains about 4,000 sentences, which annotated between drug and adverse effects. So here we have only a cause relation, and we want to explore how these sentences can be used to actually extract the same relations, cause and treat, between food and disease entities. And for this purpose, we have annotated a dataset containing 600 sentences with food and disease entities. And this dataset is publicly available, and we refer to it as the food disease dataset. So in order to enable the transfer learning from the biomedical domain to these food and disease entities, we propose a specific preprocessing, which entails masking the occurrence of the food and disease entities. So the model doesn't actually learn the relations between specific types of entities, but instead uses the context words which express the relations. So then we can look for this specific pattern between other types of entities. And Saffron actually also entails fine-tuning of BERT, Roberta, and BioBERT models on the source dataset, so the crowd truth and the adverse drug events dataset. And this is then tested on the food disease dataset. And we treat the relation extraction task as a binary classification with each model producing a 0 or a 1, indicating the existence or present and the existence or non-presence of a single relation, cause and treat. And the best models achieve a macro average Stefan score of 0.84 and 0.9 for the cause and treat relations. Now, having this named entity recognition, named entity linking, and relation extraction models, we have been able to integrate them into a pipeline, which we refer to as Foodies, or a food disease relation mining pipeline. And this pipeline is supposed to be used for semi-automatic relation mining, meaning that the pipeline can automatically find relations between food and disease entities from biomedical scientific abstracts, but we still expect the help from experts to actually curate these annotations. So the pipeline is able to extract cause or treat relations between food and disease entities, and also link these entities to different knowledge bases in the biomedical and the food domain. So this is some general overview of the pipeline. We start with querying PubMed for to obtain scientific abstracts related to a certain keywords. And then we apply named entity recognition and named entity linking methods to extract food entities and disease entities, and also link them to external knowledge bases. Then we have the step of sentence relevance filtering, which involves actually finding from which sentences we can reliably extract the relations. Then these sentences are fed into the relation classification component, which determines the relation described in one sentence. And then in the final relation determination step, we produce a single relation between two entities based on all of the evidence that has been collected in the single sentences. So for the food disease pipeline specifically, we use a voting scheme based on some of the methods that we have developed for named entity recognition. And then we use the Sabre model for extracting the disease entities and linking them to the disease ontology. And finally, we use Saffron to find the cause or treat relations. So Sabre stands for sequence annotator for biomedical entities and relation. It is capable of performing both named entity recognition and named entity linking, and it is based on neural network architecture composed of bidirectional long short-term memory and conditional random fields. And it provides pre-trained named entity recognition models for identifying diseases, genes, organisms, and chemicals, and it can link the disease concepts to the disease ontology and the chemicals entities to PubChem. On the other side, we are using the methods that we have developed for food named entity recognition. However, since both Butter and Foodner are corpus-based methods that are trained on the FoodBased Corpus, and the FoodBased Corpus is made up of recipe data, when we apply it to scientific text, it doesn't generalize well, and it typically produces a lot of false positive entities that might be other biomedical entities such as diseases or chemicals. And this actually happens because the model hasn't even seen this in recipes. And on the other side, the dictionary or rule-based methods that we have also have their limitations. Typically, they produce partial matches, such as in the example with avocado oil. If only avocado is present in the dictionary, then this will produce a partial match, and then it might miss some entities that are not present in the dictionary, and this is the example with the salt entity, which has not been extracted in this case. So to go around some of these limitations, we are using this kind of voting scheme, which essentially implies that we are applying for named entity recognition models, so FoodNer, Butter, and two dictionary-based models, which are using the names of food entities in Foodie. So we have non-scientific and scientific names. And on top of this, we built these two dictionary-based models that simply do string matching. And also, since in Foodie we have identifiers to Wikipedia and the NCBI taxonomy and ITIS, we can also, to some extent, do named entity linking based on the identifiers present in the Foodie. And we are also using all of the named entity linking models provided by FoodNer. So we have links to Foodons, Nomad City, Hansard, in the Hansard taxonomy. And the food voting scheme actually says that if we have a token which is a candidate to be a food entity, we say that this token is actually a food entity if at least two of the FoodNer, Butter, or Foodie non-scientific models agree that this is a food entity, or it can be the case that the scientific model from Foodie says that this is a food entity, and we are actually always relying on these models to produce reliable results, since we don't have scientific names in the FoodBased corpus, so Butter and FoodNer are not capable of extracting such entities. And the third option is that FoodNer has been able to link this entity to one of the three knowledge bases, Foodons, Nomad City, or the Hansard clauses. So in this case, we also rely on the prediction from these models. And we additionally do some post-processing and say that this token is not too general to be useful, or that we say that it has to contain a noun. And in the meantime, we are also working on developing this corpus, which will have on the annotations on scientific data, so we don't have to rely on 4 models to do the job, but in the meantime, this is what we are using. And then we have the sentence relevance filtering step, where we identify from which sentences we are going to derive the relations. And here we have a problem, because if we have 2 entities occurring in one sentence, such as in the example, excessive salt intake increases the risk of heart disease. From this concrete example, we can reliably say that salt causes heart disease, but if this sentence is expressed in a different manner, such as we hypothesize that excessive salt intake increases risk of heart disease, then if this hypothesis turns out not to be true, then we might have an incorrect relation, and also is the case if the relation actually expresses part of the methodology that is used to determine if this observation is correct. So what we want to do is filter out this kind of sentences, so hypothesis and method, and only find sentences which express facts or analysis. So for this purpose, we train another model which performs 4-way classification into these types of sentences, and this is the conditions that a sentence needs to pass in order for it to be used for the relation extraction step. So it has to contain at least 1 disease entity, 1 food entity, and it has to express facts or analysis. Now, all of these sentences are fed into another voting scheme, which performs relation extraction. And here we are using the Saffron models, which produce the best results. And these are the BioBERT and Roberta models trained on the crowd truth and food disease datasets. And here we simply say that say a relation is a cause relation if at least 3 of the classifiers say that this is a cause relation, and at a maximum of 1 trait classifier identifies the trait relations. However, these 3 and 1 are parameters that can be given to the pipeline so that you can essentially make a trade-off between precision and recall. So this is the number of relations that we have been able to identify by processing 80,000 abstracts, and these are only actually the relations that can be linked to the different knowledge bases. So we have the food entities linked to Foodons, Nomad-City, Hansard, and then Foodie, and ITs, Wikipedia, and CBIT, which are actually only the identifiers which are present in the Foodie. And then from the identifiers from the disease ontologies produced by the SABRE model, we can also find mappings to Nomad-City, UMLS, NCIT, OMM, EFO, and MESH. And here you can see the number of relations from the cause relations on the left side and the trait relations on the right side. So in a similar manner, we have also worked on producing another pipeline which finds relations between food and chemical entities. And here we are using the same models for the sentence relevance filtering, the named entity recognition and named entity linking, with the difference that the named entity recognition and linking methods now find chemical entities and link them to PubChem instead of the disease ontology. And then for relation classification, we have developed another method which we call FoodChem. And this method can extract contains relations between food and chemical entities. The relation extraction task is again treated as a binary classification problem, and we perform fine-tuning of BERT, BioBERT, and Roberta models. And in this case, the BioBERT model achieves the best results with a macro average F1 score of 0.9. And this is currently under review. So applying these 2 pipelines and also another one which actually extracts relations between chemical and disease entities, again using the Saffron models and the SABRE model for finding the disease entities and the chemical entities. We have produced another case study which processes about 40,000 abstracts to find relations for the milk entity more specifically. And on this slide, I have this large graph which contains all of the relations that the pipelines have been able to capture. And on the right side, we have the Eagle network for milk. And in this case, the green nodes represent food entities, and the blue ones represent chemicals, and the red ones represent diseases. And on the other hand, the blue edges represent the contains relation, the green ones represent the treat relation, and the red ones represent the disease relation. And we can see that this is actually kind of a really big mess. And so what we need now to do is find experts which will help us to make sense of it, to see which of these relations are already known, which are false positives, and which actually open up directions for future research in biochemistry. And now we would like to also link this to recipes to see the impact of eating this type of food on the health of the people, and also other applications. So these are the references to all of the things that we have talked about in this presentation, starting with Dr. Nair and Stanford, and all the way to Foodies and FoodChem, which are not even published yet. So yeah, I will now direct this to Tome to wrap up.
Okay, Gjorgjina, please stop your sharing just to, we kept only 2 or 3 slides and we are going. Okay, thank you. Thank you again for the nice presentation and helping me. Okay, so I think you can see the slides, right, where Gjorgjina ended. Yes?
Yes.
Yeah. Okay. So actually, this was our experience. We are sharing our journey starting from 2017 till now, and what we believe that we can do next, and different kinds of methods. Like, thank you all people for the question in the chat. Like, actually, we would like also to say that there is also an European Food Safety Authority supported initiative, which is extracting and annotating food name entities from scientific literature, which is the objective to prepare methodologies for creating training data sets of annotated documents and a tool for correcting any false annotation by domain experts. I saw that Karsten is here. Hi, Karsten. And we discussed a lot on this topic. So the idea is like how we can reuse some of this, how we can extend that all this. As Gjorgjina said, like we have the recipes, but we are struggling in scientific abstracts. So how we can make this fusion of different landscape of writing styles together in order to have more comprehensive, like annotated corpus. And actually the objective and the call of EXA was like providing annotated corpus, which actually can be reused for training different kind of models. The project started in May 2021, which is actually with duration of 15 months. We have some results we are discussing already with EFSA. So in the next few months, we are already planning to publish some other annotated corpuses with regard to different semantic different semantic resources which can be utilized and explored, like between food and all other like environment and the health. We would like also to thank a lot of European projects, a lot of Slovenian national projects, a lot of institutions that allow us like to have this knowledge on NLP and working in this kind of topic. You can find like several resources here. And actually, these are the key players of the team. Today I'm here with Gjorgjina, but actually we have a lot of other contributors who are helping us. You already met Gjorgjina. Gordana is doing an amazing job when this information is transferring to knowledge. So she's more like building on the top of this like machine learning approaches that can reuse this extracted information in order to predict something which is related to the human health, especially like the food consumption, macronutrient data, not using these classical statistical approaches. Eva is here with us like as a domain expert. She always answers us like a lot of questions. We don't understand like the domain or what is important to be extracted or not. We have Rista, which is our like external collaborator from the Faculty of Computer Science and Engineering from North Macedonia, me and our like supervisor, Professor Barbara Korošić-Seljak, who is actually leading this group, and she's helping us a lot to make this effort. If you have some questions, please feel free to ask us. And we have 10 days left to our workshops, which will be at IEEE Big Data. So if you have something that can be submitted there, you are welcome to contribute. It's a third workshop related to big food, nutrition, and environment data management and analysis. So 10 days left. If you have something that can be shared, like a short paper, poster, or a regular paper, please submit to this workshop. And of course, if you are interested for any news from our group, follow us on our Twitter account. Thank you.